Good day, my students, and welcome to another class on digital systems. We are going to be having our fourth lesson today, and our fourth lesson is titled Boolean Algebra. In our last class, we saw different kinds of logic gates. We saw the OR gates, the AND gates, and the NOT gate, which are the principal gates that we have. From these three gates, we had the NAND gate, the NOR gate, the exclusive OR, and the exclusive NOR gates, making it all about 7 gates. Today we want to look at how to describe logic circuits algebraically, that is mathematically, because any logic circuit, no matter how complex, may be completely described using the Boolean operations, because the OR, and NOT circuits are the basic building blocks of any digital systems. So let's take for an instance a logic gate that has an AND gate and an OR gate. OR gate. We have 2 legs. So assuming you have input A, input B, and input C, what will be the value at X? So here we have AB, because this is an AND gate, so you have AB here, and this is an OR gate, so we have the C coming to the second leg. So the answer here will be AB and C. AB and C. So this is how we express it. And we can also have it in the reverse form. We could have the OR gate, okay, and then we have the NAND gate. So you have A, B, and C, and then we have A and B. So the value at X output will be A and B in brackets and C. A or B rather and C. So this is the value. So if an expression contains both AND and OR operation, the AND operation is performed first. Like in this case, the AB is performed first before you OR it to the value of C. Unless, of course, there's it is in parentheses, as in the expression, such as in this expression of A plus B. So you have to perform the one in the parentheses before you can come outside and now do that of the what? Of the other expression. So, for example, if A is equals to 1, B is equals to 1, and C is equals to 0, for example, so you have to do 1.1 plus C. So you do this first. So the answer is 1 or 1 is equals to what? 1. So X is what? Equals to 1. So here we have 1 or 1 and 1. So you perform the value in the bracket first. 1 and 1 is 1. And then you have and 1. So 1 and 1 is equals to 1. Remembering our truth table for both the AND function and the OR function. Remember, this is algebra. This is Boolean algebra, not mathematical algebra. So 1 plus 1 is not 2 in this case. Remember, in the last class, this represents logic levels of high or low. We want to look at circuits containing inverters. Circuits containing inverters. I hope you remember what inverter is. That is the NOT gate. The NOT. Remember the symbol? Inversion. So circuits containing what? Inverters. Whenever inverter is present in the logic circuit diagram, its output expression is simply equal to the input expression with a prime or bar over it. Okay? So which means if you have an A here The expression here is A prime or A bar, and choose whatever means you wish to represent it. So let's say we have another circuit with 3 inputs. This is a 3-input AND gate, and it contains an inverter here. Okay, and then we also have an OR gate, which also contains an inverter. This should be a 2-input OR gate. Okay, so this is A, B, C, and then D. Okay, so this means it is start from here with a small knot. So it starts after this place. So here we can now have it together and to an AND gate. So we want to see the value for x. Remember, we're trying to express this circuit algebraically. Okay, what is the bit the value? So having looked at these gates, we have an AND gate, we have the OR gate, and then finally an AND gate. So the value here, when the A crosses the inverter, we have A prime. And then the B and the C all will be AND together. So we have the A prime, B, C. For this case, the A will start from here. So the A goes into this OR gate, and then we have D. So we have A or D. Now, this A or D, we have to go through an inverter again. So we have all A plus D with a bar. Finally, ends up being what? AND together. So our value at the output, x, will be A prime BC dot A plus D bar. So this is the value expressed. So when you have, if when you are given the values of A could be 0, B could be 1, C could be 1, and D could be 1 also. So you just put it inside here, having that A is 0, being inverted, you have 1, dot B 1, C 1, and then A is what? 0 plus 1, all inverted. So the value of this is 1, and 0 plus 1, that is, or 1 is 1. Inverted is 0. So 1 and 0 is what? 0. So our value here will be 0. Okay? So this will be the logic 0. So this is how we deal with circuits containing inverters. Once the Boolean expression for a circuit output has been obtained, the output logic level can be determined for any set of input levels, just like I've explained above. Let us see how we can determine output level from a diagram. That is, what I mean is how we can implement circuits from a Boolean expression. When we have the expression, the Boolean expression given, how do we derive the circuit from the Boolean expression? Okay. So from this Boolean expression, or rather from this logic circuit, we could get the Boolean expression. Now, what if we are given the Boolean expression? Can we get the circuit that is obtained therein? So for example, let's say we have a y is equals to AC plus BC prime plus say A prime BC. So let us have it this way. Let's say this is the OR, because everything is all together. Let's say this is the Y. So we have AC, we have BC prime, then we have A prime BC. So this is just the general outlook, how it's going to look like. But we know that there are more functions. We can't represent it in this way. So we have to further break it down. Because there are AND gates contained here, there are inverter circuits contained here. But in general, the rules for evaluating Boolean expressions, number one is you first of all perform all inversions of single terms. That is from 0 to 1 or 1 to 0. Then you perform all operations within the parentheses. Number three, you perform an AND operation before an OR operation, unless parentheses indicates otherwise. Now, if an expression has a bar over it, you perform the operation of the expression first, then you can now add it to the results. So in other words, once you have the parentheses, for example, you should perform this parenthesis. If you have an AND, the AND should be performed before going out of the results. So these are some of the rules. So you don't have, just like in mathematics, it is somewhat similar to the board mass. If you remember the board mass, okay? Some say brackets first, then off, division, multiplication, addition, and subtraction. It looks like that. So if you have the board mass in mind while evaluating Boolean expressions, it will help you. So it can guide you. So you don't have, for example, 2 plus 3 or 2 plus 3 times 4. Supposed to be 2 plus 3, for example, 5 times 4, which is answer should be 20. So you don't go and say 3 times 4, 12, and I say 2 plus 12, 14. So if there is no rules like that, you have multiple and different answers. So if you know mathematics very well, you know the board mass, that will help you to also evaluate the Boolean expression properly. So in order to get the final circuit, back to the circuit, we have to break this further down, okay? So how do we do that? We take it step by step. We know this tells us that it was all together. So our final circuit will definitely have to be something like an OR, okay? So let's keep it here. So we have A and C. Let's say we have this. Okay, so this is an AND gate, and then we have another AND gate. Okay, this is how you read from the answer, rather from the Boolean expression. Now look at this. There is a prime. So for the C, there should be a prime, and then we also have the third one, A, B, and C. So let's say we have 3 values here, A, B, and C. Okay? So let's assume that this is a circuit with about 3 inputs and gates. This is a C. So for this output here, we have A, we have AC, we have another one that will give us BC. So we should have here B, and then C. Okay, and this C has to go through a prime. Okay, so we have an output. So this C, start from here, goes through here, we have the C prime, and together we have the C prime. And then we have the A prime. So our A can also be tagged from here. A, B, and C. So the A has to go through an inverter. Okay. And then the B has to be tagged from here as well. And then the C as well. So here we can now have A prime, B, and then we have have our C. You can see these answers are here now. So all these will finally sum up into our AND, or rather our OR gate. So that we can now have Y is equals to AC plus BC prime plus A prime BC. Okay, so we have implemented the logic circuit from the Boolean expression. Can you see that? We have implemented it. So we have 3 gates, 3 AND gates, 1 OR gate, and 2 inverters present in this circuit. So for us to achieve this result, these are the logic gates. Logic gates number 1, number 2, number 3, and number 4. And then of course number 5 and number 6. We need about 6 gates to achieve this Boolean expression. Okay? So generally there are other examples and quizzes in your content which I expect you to go through it and practice more. There are also, the next topic here will be the Boolean theorem. So I'd like you to read up the Boolean theorem. There are about 15 theorems. These theorems help to simplify complex circuits into a much smaller ones. In other words, this circuit that requires up to 6 gates to implement. When you arm yourself with the Boolean theorem from 1 to 15 and from 15 beyond, this circuit can be further compressed. Instead of using about 6 gates, you may end up using about 2 or 3 gates. That's what the Boolean theorem will do. So theorem 16 and theorem 17 is known as De Morgan's theorem. It was developed by a man called De Morgan. So this De Morgan's theorem is extremely useful in simplified expressions in which a product or sum of variable is inverted. So when you go through your text or go through your material, you will see this theorem even with theorem 18 and 19. Okay, there has a 3-variable De Morgan's theorem. When you go through them, this will help you to further simplify such complex Boolean logic circuits into Boolean expressions, or from Boolean expressions to a simplified logic circuit. I hope you understand this class. Go through your assignments and quizzes until you see next time. Have a nice day. Thank you.